It is a pleasure to introduce our last speaker today, which is Giovanni Rosso from Concordia University in Canada, who will speak about Overconvergent Eichler Shimura for families of Siegel modular forms.
Okay, yeah, thank you very much for the invitation. I would have loved to visit Buenos Aires, but for another time. In any case, so far I enjoyed the conference a lot. So what I'm going to talk about today, Overconvergent Eichler Shimura for Siegel form. I think it's better to start with classical form and see how is the situation for GL2. So let me start with MK gamma in the space of modular form of weight K and the level gamma. So what is this space? It's the set of all functions f on the upper half plane into C that are holomorphic. And the other condition I want to require is that f of gamma z is equal to Cz plus d to the k f of z for every gamma in my congruent subgroup gamma. So it's the set of plus another condition at infinity that I'm going to ignore for now. So modular form are nothing else than function on the upper half plane that transform nicely under the action of gamma, where gamma here is a subgroup of SL2 of Z. So the Eichler-Shimura isomorphism, the classical one by Eichler and Shimura, somehow is interpreting this modular form that I define in complex term as some geometric object. So the first thing to notice is that, for example, suppose that K is equal to 2, and we're going to consider the following curves, X, which is H modulo gamma. This is an algebraic curve, Riemann surface, algebraic curve. Priori is a Riemann surface, but is even defined over a number field. And we see that if I consider dz, the invariant differential on H, what do I get? I consider f of z dz, and I notice that this is gamma invariant. Gamma invariant one form on X. Okay, and so what this is telling us is somehow that we can, starting from a modular form, we can construct this new object, which is a differential form. And so this is going to be an element in the H1 theorem of X with coefficient in C, let's say. So it's a one form. Okay, and the Eichler-Shimura relation. Isomorphism. What does it do? It tells us that H, if I consider this space, H1 theorem of X, C, this decompose as a K module. So the important thing here is that the action respects the AK action, that the isomorphisms respect the AK action. This H1 theorem decomposes the space of modular form of level gamma in direct sum with the space of Gas form, always of level gamma and weight K, but are anti-holomorphic. So I put a bar to denote that these are anti-holomorphic things. So somehow this is telling us that if you are looking for modular form, we can all look inside the H1 theorem. But there is a second definition of modular form, a second geometric interpretation. The second geometric interpretation that I'm going to use is that I can construct omega over X, a line bundle. So it's, well, it's literally something that is locally X, such that I can write MK gamma to be the global section of the sheaf omega over X bar where what is the Rx bar? This is a compactification of X. The problem is that the X is an open curve somehow. It's missing some points, so I compactify, I extend my line bundle there. And modular form can be interpreted as section of this. And so somehow this is reasonable because here there should be, let me denote the dependence from K. I'm getting a bit, yeah, there should be a 2. But this is true in general, more generally, for more general coefficient. You just need to change this with a representation of GL2. And so now I have this sort of two different geometric interpretation, either as one form with values in C or in some particular representation, or a section of coherent line bundle. So I have a sort of local system interpretation and another coherent interpretation. And these two can be put together. And let me put them together periodically. So let me tell you something that Faltings did. Let me consider sim k minus 2 of QP to be the set of homogeneous polynomial of degree of weight 2. Oh, wait. Let me fix P a prime number. For now on, P is a prime number. And then I'm going to consider the set of homogeneous polynomial of degree k minus 2. And a theorem of Faltings is saying that I have periodic Eichler Shimura due to Faltings. Is that I can define the following filtration. Omega k, tensor over QP. CP twisted by, let me get the index correct, k plus 1. This is a subobject of the étale cohomology of X, with coefficient in k minus 2, coefficient in QP, extend with CP, and let me put a twist here. This twist just denotes the Galois action, it's not very important. And as a quotient, I have again exactly this space omega k and tensor over QP with CP. And this is surjective. So Eichler Shimura by Faltings is telling us that we can decompose the étale cohomology of this local system, and we get, well, here I should have the compactification, and we can decompose this in two pieces. This is the theorem of Tate that every CP representation can be decomposed somehow very simply. But this simple part, when we look at them as a module, are exactly the parts that come from the modular form, or in this case, the Arcer duality. Here there should be probably +2, the dual of the modular forms. So what people have been doing it, you can do everything in family. Family, for example, we can define a sheaf decay, a local system of X. Maybe it's a good moment to introduce maybe the weight. Let me define W, the weight space. What is it? It's nothing else than the continuous homomorphism between ZP star and CP star. Homomorphism of group, and all the K weight of modular form can be embedded inside here. If I can consider the morphism K that map Z to Z to the K. This is a well-defined map. And so the weight space is a p-adic space. It's practically a bunch of balls that contains all the weight of modular form. So the basic idea in p-adic deformation is that when I have a bunch of modular form, I want to deform them p-adically. We have seen plenty of talks today about this. And so I can construct two objects. One is decay, which is a local system on X. I can construct another, here K is the generic weight of W. of my weight space, and I define these two objects, a local system and a coherent sheaf. Then I have this omega kappa, which is a sheaf on, not on X, but on XV, which is a neighbor of the ordinary locus. So what I'm doing, I'm taking my X, I remove some points that have a reduction modulo P, a super single elliptic curve, and then I take a neighbor of this new space. And so I have these two objects and a theorem that is due to Andreatta, Iovita, Stevens, and Oyevsky, Hansen, Johansson, is that if we consider the cohomology of X with values in this d kappa, we have a natural map to this coherent cohomology, omega kappa. There exists a map like this, Eke-Gala equivariant. Interpolating the morphisms of Faltings. For different cases. So what we want to do today, we are going to show that we can do something similar for Siegel modular form. And before doing this, let me sketch a second the naive idea behind Falting's theorem. How does Faltings more or less try to prove these things? We start with sin k minus 2, and this is an algebraic representation of SL2. And omega k is kinda of a, well, is a piece of a GM torso. So it's practically a representation of GM. So naively, we can decompose sin k minus 2. This is just xk minus 2, all my homogeneous stuff, yk minus 2. And naively, I would like, let me put a minus 2 also here. I would like to consider the following map. I project to the vector xk minus 2. And if I look GM inside SL2, I have my T, it is mapped into T minus 1. Somehow this is what should give me an explanation why I have this type of map, because I have something here and I can project on this IF space vector that behaves a bit like a weight k minus 2. The things are not so easy because, let me write it in red. Somehow here we are comparing apples and pears because sin k minus 2 is a local system. While the other one, omega k, is a coherent sheaf. So I cannot compare these two objects because a priori they are living in two different spaces. So the trick is that to consider X pro Coleman et al. Is kind of, I want to consider all the étale, I would like to consider all the étale cover of X. The problem is that when I change the level, for example, if I have a smaller gamma prime, the map between X associated with gamma prime and X associated with gamma is not étale at the cusp. So I need to find a substitute for this morphism not being étale. These morphisms are log Coleman et al. And so this is what we have and what we work on. This is a site. So somehow we can think of this two local system and two sheaf on this site. And if I consider something like sin k minus 2 tensor OX pk et al. Then I have omega k minus 2. I can just look at these two sheaf on this new site, but as a sheaf of OX pro et al. Modules. Well, then I have this map, more or less. Now I can compare it, and I more or less at this map, and just notice that this map is very twisted. I will say a bit more later, maybe, about how this map is defined, but the idea is that it's not this very simple map. You are somehow projecting all of this. They go to a single line where the action is given by k, but somehow every of these things is somehow modified by a function, by an element of this space that has a certain transformation property that we want for the group SL2. Okay, and so let me talk about the result of today. As I told you, as I brought in the beginning, this is joint work with Hansheng, Diao, and Ju-Feng Wu. So what we are going to start, we start with Siegel modular form. So what are Siegel modular forms? I start with, let me call it WK, an algebraic representation of GLG. And here K is a tuples K1 Kg. If I suppose that W is an irreducible algebraic representation, this Ki can be this is characterized uniquely by this weight, that there must be dominant. So a weight K modular Siegel modular form is nothing else than a function from the Siegel upper half plane inside WK that satisfies a similar transformation property as before. F of gamma Z is going to be equal to, let me call it rho chi of, did I write down? Well, I can guess. AZ plus B times CZ plus D to the minus 1 times F of Z, where here Z is my upper half plane, generalization of the upper half plane, and gamma, ABCD, is a matrix in GSP 2G of Z. Okay, so this is the generalization. Somehow they are always function on some sort of generalization of the upper half plane. It's just that I need to consider not only valued in C, but valued in particular algebraic representation of GLG. And as usual, I can define MK, the space of weight K modular form. And here gamma, if you want, is not necessarily here. It can be in a small gamma is a group here. MK gamma is going to be exactly my space of modular form. And as before, I can realize it as the global section of some x bar, some sheaf omega k, where again x is h of g modulo gamma. Then I compactify it. I take a toroidal compactification. And over here, I can construct a coherent sheaf. It's not a line bundle anymore, but it's a line bundle over there, a line bundle here. And so I have this characterization. And this is the first object that we want to consider today. There is a second object. Now I start with VK, an algebraic representation of, in this case, GSP 2G. And I can construct antithetical VK, a local system. On X. And I don't need to take the compactification. I mean, you extend this, you push forward to the compactification. So what I want to compare is HD of X VK with H0 of X bar omega K, where likely there will be a small shift between the weight as before. You remember that this was a shift by 2, so technically there will be a small modification here. And here D is the dimension of the Siegel upper half space, so it's G plus 1 over 2. So I want to compare this space with this space, and they both realize Siegel modular form, and I want to see how I can compare them. And compare this, and then compare this in family. So the first things to do is, let me skip right away to the family. In this case, we consider the new weight space, which is going to be the homomorphism between ZP star to the G to CP star. So again, this is again a bunch of G-dimensional ball. G is exactly the number of variables I have, so are the one that I want to deform. The first things is that due to Ash, Stevens, Urban, and Hansen, theorem says that there exists an HD of X d kappa. Again, kappa is going to be my variable inside this weight space. And I can define a local system d kappa. And this is, well, a module to construct families, at least when they are cuspidal. Somehow I can use this space, this big cohomology, to construct families of Siegel modular form. And there is another construction by Andreatta, Iovita, Filoni. Families of modular forms, families of Siegel modular form. Can be constructed also as section of some, well, not really coherent, but some Banach sheaf. H0, again, I need to take a small locus here. I can only consider points in X that are close to the ordinary of some big sheaf omega kappa. It is, again, for cuspidal form, if you want to construct family like eigenvarieties. So what we would like to do today is to compare these two constructions. And the way to compare them is inspired by the construction of Faltings. So let me give a short recall about perfectoid Siegel variety. I can consider its infinity, which is some sort of inverse limit of X associated to where I add some level at P. I can consider congruent subgroup where my matrices here are in the subgroup where this matrix is reduced to the identity modulo P to the n. I can consider, they form an inverse system, and I can consider the inverse limit. I can now even do it for the compactification. And this is a perfectoid space. So I can consider the tower where I take smaller and smaller level at P, and I get something which is a perfectoid space. The good things of this stuff is that there is a map X that I call pi Hodge state from X infinity to the Flach variety for GSP to G. Is the Flach variety the parameterized Lagrangian subspace of dimension G in a base vector space of dimension 2G? That somehow that is defined more or less for every point X in X infinity. I have that X correspond more or less to an abelian variety, and then isomorphism gamma between the Tate module of the abelian variety, ZP to G. And I have for this X, I have the Hodge state map. That tell us that if I take TP of A, I tensor with CP, I can go into omega of A, and in my kernel I have the Lie algebra of the dual abelian variety. So in particular, once I have this isomorphism, I can consider this. Let me put here CP. I have this isomorphism. This is a nice 2G dimensional vector space thanks to this isomorphism. This Lie algebra is G dimensional, so it defines a Lagrangian subspace inside this CP vector space, so it defines a point there. So the Hodge state map sends the point X given by this gamma to the image of the Lagrangian subspace Lie of A inside this space. So it's a nice point there. So the first theorem And this is due to people. Schott constructed the first, and for the minimum quantification, Piloni and Straw extended this construction to the toroidal one and the Hodge state map there. And so what is the first stuff that we did? Theorem. Well, definition, this is due to Diao, myself, and Wu. We can define a sheaf omega kappa on X, again V, of families of Siegel modular form. Such that these are the function f in O x infinity v of, let's say, of an open U. Oops, sorry, no, this is not exactly correct because I need to put some coefficient. These are f that belongs to continuous function of weight kappa from the Iwaori of GSP2G inside the structural sheaf of X infinity. I mean, somehow these are function valued in OX is a representation of this Iwaori valued in OX modules that where the action is given by kappa. And what happened exactly in this case? When I take the pullback by gamma of f, I didn't tell you, but I have a natural action here of GSP2G of ZP. So I can act with every gamma in the Iwaori subgroup, GSP2G. When I take the pullback of my function f here, well, taking the pullback in this way is the same that applying the representation of rho kappa. Let me see if I write down the matrices precisely. I should have. Like A plus ZC minus 1 applied to F, where rho kappa is the action of gamma on this space. GSP2G on this set of this as a representation of the Iwaori. It acts by multiplication on the left, and I just denote this multiplication on the left by this. And here, what is Z? Z is a special matrices belongs to mg times g of OX infinity, obtained via pullback of the coordinate Z, let's call it Z tilde, on the flag variety. The flag variety is a point, once you fix a point in the Lagrangian, every other Lagrangian is somehow conjugated by a matrix which is in the unipotent of GSP2G. So it's characterized by G times G symmetric even matrix. So I just pull it back via the Hodge state map, and I have this function there. And then I just want to consider function in this big induction that transform like this. And the first theorem that is due to us is that, well, H0 of xv bar omega kappa, let's call it omega kappa infinity, because it's constructed with perfected methods, is exactly the same as H0 x bar infinity omega kappa equivariant. So we've given a new construction of the space of periodic modular form and families by Andreatta, Iovita, Piloni, using this infinite construction, this perfectoid method. And so this is our first theorem. Our second theorem is the following. There is an Eichler Shimura map that goes from HD of my X pro Kummer et al. Technically. Let me get to the twist right. The kappa, I suppose, twisted by the degree inside our sheaf H0 XV omega infinity kappa. Let me call it this ES kappa, which is Eichen-Galois equivariant. Where, I mean, there is no action on Galois cohomology, but there is some action on this Procummer-étale cohomology. This you should just think is the cohomology of the local system. I just put Procummer-étale because later to tell you how to construct this. We will need the Procummer-étale site. But the idea is somehow that, as before, all the stuff that happens in for a fixed weight happen also in family. And let me tell you something more for the theorem. If kappa is a classical weight, K1, Kg, then the image of the Eichler-Shimura kappa is contained in mk gamma. So somehow this map factors to the classical form when k is a classical weight. And this is going to be easy to see once I tell you a bit how to compare this. Well, let me sketch then the key to the comparison. The kappa is a representation of the worry of GSP2G. And omega kappa infinity is a representation, more or less, of the worry of GLG. And indeed, because you can send GLG inside GSP4, GSP2G, I send a matrix gamma to gamma and gamma transpose inverse. Is exactly the TT minus 1 that I did before, just now we have matrices. So morally, we have inside the kappa, there exists an element that I'm going to call E highest, which is practically interpolating all the highest weight vector of the representation that I think I call VK, the representation of GSP2G that were appearing, I call it. There is something that interpolates all this VK. If you think of the example of GL2, I have this x to the k minus 2. Well, it would be x to the kappa, or if you want, kappa of x. So, there is an analytic function of this weight kappa that interpolates all these x to the k. And you can do something similarly for this big representation. And the good thing is that this EI is stable for GLG. Well, it's stable for the worry of GLG because it's just the action of the worry. So it's the idea for this map, Eichler-Shimura K, is that we have a map from decay to omega infinity kappa. Again, I need to tensor with the Procummer-étale site and complete. That somehow projects, these are distribution, mu, and I'm going to integrate mu against the highest weight vector. And then I look at it just as a representation of the worry. Is also the highest weight vector for the representation of GLG. So somehow what I'm doing, I'm kind of projecting after twisting with this funny coefficient against the highest weight vector. And this is somehow how the classical Eichler-Shimura map is also constructed. And this is the key to the construction of our ES kappa, because once we have this, yes, okay, let's call this eta kappa. Once I have the map eta kappa at the level of sheaf, I can induce ESK on cohomology. So I get naturally a map from the HD of X of these things here to the HD of Coleman et al. X bar infinity kappa. And from here, I have the right vector sequence that goes to the coherent cohomology, again, of my sheaf. Here, there should be some V. Omega infinity kappa. Okay. And yeah, I'm already 1 minute above the time, so I think this is a good moment to finish the talk.
Okay, so let's thank the speaker. Are there any questions or comments?
So when you say the image is gonna be inside the kind of the classical space,
Yeah.
What are the conditions on the weight you have?
What kind of, I mean, what I'm saying is that suppose that here kappa is not the general weight, it's a classical weight, and here you take the overconvergent distribution of weight k fixed, and here you take the sheaf of overconvergent form.
So
mysteriously,
for classical weight, you mean?
Yeah, classical dominant algebraic.
So you can you don't require the weight correspond to holomorphic discrete series, but any.
No, even it's kind of automatic. I mean, yes, because I want here to have some. Let's say that I want to have some. I want V kappa to come from a local system, and this forces the weight to be some sort of quite dominant, I would say.
Okay, so you.
At least when you move it back to this K, yeah.
So in some cases there is no result about like a classicity.
Yeah, I mean somehow if you want, no, maybe I didn't understand exactly the question, but the point is that I'm projecting against over this highest weight vector, which is algebraic. So when I consider somehow this analytic distribution, and then I project again against an algebraic vector, I get back the algebraic things. It's exactly the same things that happen for GL2. So if you want, my guess is that the co-kernel of this map, if you look it in general, is supported only on integers weight, which is coherent with what happened for GL2 at least. So. No, it's not the answer either.
So for that, because so when the weight is classical, and I think for the classicity result you have some more.
When the weight, yeah, somehow.
So so this thing actually is so it's beyond the cases where we have.
Yeah. I mean, if in small slope is surjective because you have this control theorem. But the interesting stuff is that even though the space is very large, the image of this map is very small when K is algebraic. It's even stronger than the control theorem if you want.
I see. Thank you.
In some sense, it's sad, no problem, because you miss all this interesting overconvergent form, but yeah.
So you are not.
I think, Giovanni, if I understood the question, if you in the classical case you cannot hit weight one forms, right? Because
there
are limiting points, but they don't get it there. So,
okay.
for example, if you are in GSP4, then you cannot hit weight two forms because they are like this limit of discrete series. They're not really discrete series. I think this was the question.
Okay. No. Then definitely, here I can only get, because here will be kappa plus G plus 1. I didn't write it. So somehow what I want is classical the weight for the local system. And so the classical weight for local system, for example, is C. The lowest weight for GL2 correspond to formal weight 2. So yeah, I'm missing all the, I mean, I see them periodically, but it's not in this classicality. Here, this kappa is really the weight here, not of the coherent part.
Yes. So Daniel, do you want to ask a question?
Oh no, you construct this morphism for you are not restricting to the finite slope part. No,
no, there is no need to, because they are defined. I mean, they are defined on these modules. Yeah, there is no need to restrict them.
So
if you want to construct on the eigenvariety, then you need to restrict to the small part, putting Caspidal condition and so on. But yeah.
But in the small part, you can say more properties of this map, for example. Or in the
it's
not
small,
finite,
it's surjective. I will guess it's surjective. I hope that we can split it HD as sum of 2 to the G copies of H0 as modules, but this is a bit trickier.
Oh, yeah.
Like the original theorem of Eichler and Shimura is that you have a decomposition plus form plus modular form. So ideally, I would like to say that I have 2 to the G copy of this as a module inside here, but this is tricky. This requires higher here.
So is the kernel of the finite slope part of this morphism? Can you decompose it as a?
What I hope I can do, I can. This is why I had this image there. I can probably opt to construct a map from the kernel of this Eichler Shimura to the H. I write my Siegel variety in 4 pieces. This is for GSP4. This is the usual ordinary locus. But when I'm at the a priori level, you know that for gamma naught of P, you can have an elliptic curve with a P torsion subgroup. It can be multiplicative of étale. So I can somehow partition this space into 4 pieces according if my subgroup over the P square is multiplicative, multiplicative, multiplicative étale, 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 or étale multiplicative. My hope is that doing some sort of twisting this map, every element, all of these 4 points correspond to 4 different elements in the Weil group. So my hope will be that I can twist this map. A priori, the sheaf is defined everywhere. Then I twist this map by the element on the Weil group that gives me, for example, this part. And over here, I will get another map from the HD to the sheaf, omega twisted over here. And by definition, more or less is contained in the kernel of the previous one. And I hope that this map like this will go not this time not to the H0, but to the H1, because I'm going to put some sort of compact support condition that raise the cohomology from, these are some sort of affinoid, so they have no cohomology, but if I put some compact support condition, I can expect higher cohomology. So I hope to get a map from the kernel of this Eichler Shimura to the H1 of a sheaf over here. And then from the kernel of this other map, I hope to get something to the H2 here, and then from the last stuff to the H3 here. And ideally, if in small slope, this should give me like the exact decomposition of the HD small slope in these pieces. But yeah, this is a long, long way. Just constructing the map is not trivial.
Can you say something about the infinite slope part?
Definitely not. No idea. No, honestly, we didn't even think about it because, I mean, already we cannot say anything on this, any single object. I mean, the map is equivariant, so it sends infinite slope to infinite slope, but more than this, no.
Are there any other questions or comments for the speaker? Okay, if not, let's thank Giovanni again.
Thanks for listening.